Welcome to clickmyproject.com.
Our product title is a 14-bit 250 MSS IF sampling pipelined ADC in 180 nm CMOS process. Let we see our product abstract. Our process implemented in ADC is measured under different input frequency with a sampling rate of 250 MSS, and it consumes 300 milliwatts from a 1.8 voltage supply. For the 30 MHz input, the measured SFDR and SNDR of the ADC. The ADC process we have fabricated in the 180 nm CMOS process we library created, and then we implemented the ADC process, improved the SHA with optimize the bootstrap switches to achieve high sampling linearity the input frequency range. And then our process main challenge of the IF sampling ADC is linearity distortion of high input frequencies, the SFDR, which is one of the great importance of the wireless communication process. Signal we get the weak signal to support the detecting the weak and peak signals process. We are using the SFDR process, and then the ADC process is a restriction of the front end sample hold process, and the non-linearity introduced the transfer the final digit output process. We get the secondary of the final gain error process, and then ADC transfer functions the capacitor mismatches between the both capacitors, the feedback capacitors, and the unique jump of the ADC transfer functions. Either we are using the jump or unique process, we have finally get the insufficient output, introduce the limited settle the distortion SFDF process. Our main thing of the process, we how should minimize and optimize the process for the speed and then power process, and then the strong process of the sampling we get the efficiency of the frequency with getting the transfer the process. We are using the ADC process. Now we are going to discuss about our process flow diagrams. Our process ADC, we have designed the pipeline design of the process. We have presented in ADC we sample and hold amplifier of the utilization the design improve the sampling linearity. So we are going to the pipeline ADC stages. So we have designed 1 to 5 stages. We are getting the analog to digital converters with sampling and hold the amplifier using. So in this process, sample and hold the process, we have using the get the input analog signals. We are using the input frequency, even though it may increase in the power and noise of the ADC. Because of the SHA less architecture of has difficulties achieving the high SFDR for IF sampling applications with the fast challenging input signals. Though we have easily detect the errors and the complicated input networks, multi-bit stage can using the however the high bit number of limited is offset comparators. So we are using the comparators of the flash ADCs. In this design we have using the 4-bit flash stage and the 3-bit stage and the 2.5 bit stage. We have defined the step by step the stages as a development low cost foreground. The calibration is performed in the comparator sections, and then we are getting the reference voltage from here. The reference current and voltage we are dedicated the 4 calibration degrees the capacitor size from the matching limitation and the noise limitation and the power consumptions. Additionally, the proposed partial non-overlapping process increasing the reside bandwidth requirement in the amplifiers, and the power also we get the improving the process. And then we are going to multiply process. So in the comparing process, the clockwise we are increased, and then we going to the analog to front end of the ADC process. the voltage dependent the capacitance process in the multiplayer circuits. We are considering the fact of the error organization and current charging of the analog mux process, and then the process the linear corruption of effect become the even more source of the input frequency increase and the factor of the capacitance from the input node to during the whole space to sampling and capacitor process. We are getting the same process stage one by one. We get the process purely we got the process in digital process. We give the input for analogs, we get the process digital process zeros as ones. Let me see our process running procedure. We have designed the ADC for Tanner EDA 13 version, and we have designed the cell 0. So first of all we create the some project IDs, and then we design the cell process also. So we have designed the in the cell 0 the ADC process, and then we are going to set up the process here the transient Fourier analysis. This is our process the generally and then we have given the stop and the maximum time, what are the timing we need. We are getting the process, we give it. After we are going to the running the process, we get the some waveform edit process tool open, and we get the analyzing the graphically output changes process zeros as ones. The here we are using our process analog to digital converters. So what are the analog values? We give the analog values the and we get the digital values of zeros as ones. So what are the real-time process of the sensors, whatever maybe they are giving only for analog values, and then we get the process value for digital zeros as ones. Then we'll be take the controllers as ICs, whatever the maybe the protocols, we get the only zeros as ones only. So we have main application of the any sensors real time in using the analog to digital converters. After we are using the ICs and peripherals in zeros as ones, we get the output. So we see our process split the processing. So this is process getting the analog to digitals, we get the output for digitals. This is analog input, and we get the digital output process. And then we have using the how much of the power calculation we get the process, and the timing period we have using the this process the T-space simulation tool. We are using the we get the how much times on the nodes. So what are the process we get? So we have using the 86.3 seconds time in the first we have get the output process. So we have optimized this process in analog digital converters. Thank you viewing our website.